Non-resonant antennas, problems on helical and Yagi antennas, series on antennas and wave propagation, lecture number 4.21. Helical antennas are well known for their circular polarization, whereas Yagi arrays are popular for terrestrial domestic TV reception. In the present session, we consider several problems, numerical problems on helical antennas and Yagi antennas too. Problems on helical antennas are mainly focused on directivity and beam width, whereas problems on Yagi antennas, they are concerned with dimensions of elements, spacings of the elements along with directivity. To begin with, we consider a problem, example 1. A 10-turn right-handed 1 GHz helical antenna has a diameter of 100 mm and 70 mm turn spacing. Find its half power beamwidth, gain, polarization state. This is the problem. We are asked to find beamwidth, gain, polarization state. Number of turns is given, frequency of operation is given, dia of the coil is given, and turn spacing is also given. Now let us proceed. Solution. Wavelength corresponding to 1 GHz is 300 mm. Dia is given as 100 mm. So circumference C equal to pi d. In the present case it becomes 100 pi millimeters. D is available. 100 into pi is circumference. Circumference in wavelengths is circumference divided by wavelengths. In the present case, it turns out to be 1.05. The turn spacing is given as 70 mm. In terms of wavelengths, it becomes 70 by 300. Therefore, S lambda spacing in wavelengths becomes 0.233. Given that number of turns is 10. Now, first null beamwidth we compute. It is given by this form. Fn BW is 115 over C lambda square root of 1 over ns lambda. C lambda is available, n is available, s lambda is available. Substitution and a little bit of simplification results in Fn BW as 71.75 degrees. This is Fn BW. We are asked to find half power beamwidth. Half power beamwidth is approximately equal to half of first null beamwidth. Hence, it is 71.75 degrees by 2 equal to 35.86 degrees. In the case of helical antennas, as they are low loss systems, gain and directivity both are same, almost same. So formula for directivity is 15 n s lambda c lambda square. Substituting the values for n s lambda c lambda in this expression, we get directivity as 38.53. It is also gain. Beamwidth has been computed, gain has been found. Now polarization state. Axial ratio gives information regarding the polarization. The polarization of the antenna may be linear or it may be non-linear. If it is linear, it may be horizontal, vertical, or it may be electric vector may be at some slanting angle with the horizontal. If the polarization is non-linear, it may be circular, it may be elliptical. In either case, it may be right-handed, it may be left-handed sense. So, as far as non-linear polarization is concerned, sense is also an important aspect. When we are asked to give information regarding polarization state, we have to tell about sense to when the polarization is nonlinear. So AR is 2n plus 1 over 2n. It is 1.05, nearly equal to 1. It implies the antenna is circularly polarized. When it comes to sense, as the coil is right-handed, polarization also right-handed. Sense of polarization is also right-handed. Sense depends upon the handedness of the coil. Example 2. A right-handed 30 turn lambda by 3 diameter and lambda by 5 turn spacing helical antenna is working in axial mode. Find its half power beam width, gain, polarization. Coil is right-handed, number of turns is 30, dia is lambda by 3, turn spacing is lambda by 5. Find half power beam width, gain and polarization. Solution. We know now half power beam width or gain, they require C lambda and S lambda. So first we try to find out these two quantities, C lambda, S lambda. Given that the diameter of helical antenna is lambda by 3, so the circumference becomes C equal to pi d. D is lambda by 3. So C is pi lambda by 3. The circumference in terms of wavelength becomes C lambda is C by lambda. It is equal to pi by 3 in this case. Now turn spacing. Turn spacing is given as lambda by 5. In terms of wavelengths, it becomes S by lambda. So S lambda is 1 by 5. Number of turns N is given as 30. So first null beam width, this is standard formula. In degrees is 115 over C lambda square root of 1 over NS lambda. Substitution of the values in this expression gives us first null beam width as 44.94 degrees. Half power beam width is approximately half of the first null beam width. Therefore, in the present case, half power beam width is 44.94 degrees. This is first null beam width divided by 2. It gives us half power beam width as 22.47 degrees. Helical coil is normally made with good conductor and therefore it's a lossless system. Loss resistance is negligibly small. Hence gain and directivity are same. This point we have already mentioned in the previous problem. So gain or directivity both are same. Directivity is given by 15 ns lambda C lambda square. Substitution gives us directivity or gain as 98.65. The last one, polarization state. Axial ratio 2n plus 1 by 2n. It is around 1.06. Nearly 1 means polarization is circular. And the sense of polarization, it is same as coil's handedness. Coil is given as a right-handed, therefore sense also right-handed. Another problem, example 3. A RCP axial mode helical antenna with 17 dBi gain is to work at 1.6 GHz with a turn spacing of lambda by pi. Find number of turns, turn diameter and axial ratio. Solution. It is said in the problem that the antenna is functioning in axial mode. Axial mode comes into being when circumference of helix is around 1 wavelength. So by mentioning that antenna is radiating in axial mode, he gave some information that C is around 1 wavelength. Now let us proceed with the solution. The axial mode comes into being when circumference of helix is 1 wavelength nearly. Let us suppose the circumference as 1 wavelength, C equal to lambda pi d. D is dia. So D turns out to be lambda by pi. The turn spacing lambda by pi in terms of wavelengths is 1 by pi. Spacing is given as lambda by pi. In terms of wavelength, it becomes 1 by pi. As circumference is 1 wavelength, C lambda becomes 1 because C lambda is C by lambda. Assuming C as 1 wavelength, naturally C lambda becomes 1. Now it is given that directivity is 17 dB. Hence 10 log D. This is directivity in dB, which is of course given as 17, but D is 10. D is 15 ns lambda C lambda square. Therefore 10 log 15 ns lambda C lambda whole square is 17. Solving this relation for n gives us n equal to 10.5. C lambda value is known, S lambda value is known, only n is unknown. So it is not at all difficult to find value of n. In the present case, it turns out to be 10.5. Thus the coil must have a minimum number of 11 turns. One cannot have half turn. So 11 turns. So number of turns has been determined. Now turn diameter. Turn dia is lambda by pi. If we know lambda wavelength, then it is not a big deal to find turn dia. Frequency of operation is given as 1.6. F is 1.6 gigahertz and lambda can be determined from C by F. C is 3 into 10 power 8 meters per second. Frequency is of course 1.6 gigahertz. Lambda can be determined from this relation. Once lambda is available, D can be found from this relation. Last item is axial ratio. Axial ratio is, by definition, it is 2n plus 1 by 2n. As n is 11, it turns out to be 23 by 22. It is nearly 1. So axial ratio is 1 slightly more than 1. So now we have found all the quantities that are asked to be computed. So far the discussion was on problems set around helical antennas. Now we move to problems on Aggiora arrays. Example 1. A 7-element Aggie is operated at 100 megahertz. Determine minimum number of directors, length of the array in meters, and also its gain in dB. This is a typical problem, standard problem, frequently appearing in the examinations. So let us go through it keenly, seriously. Elements of the array are one reflector, one driven element, and several directors. Usually we don't use more than one reflector. We don't go for more than one driven element. So reflector is one, driven element is one, but directors are more than one. It is obvious number of directors are 5 because number of elements is given as a 7, so directors are 5. When directors are n, assuming typical spacings, reflector spacing of 0.25 lambda and director spacing of 0.30 lambda, array length becomes L is 0.25 lambda plus 0.30 lambda, 5 minus 1. So one reflector, one driven element, and 5 directors. 1, 2, 3, 4, 5. Assuming typical spacings, reflector spacing, here it is assumed it is 0.25 lambda. Director spacing of, here it is assumed it is 0.30 lambda. Length can be easily computed. Formula is 0.25 lambda plus 0.30 lambda into 5 minus 1. It turns out to be 1.45 lambda. Wavelength corresponding to 100 megahertz is 3 meters. Hence, length of array is lambda is found as 3 meters. So, length becomes 4.35 meters. Gain of this array then can be found using the formula. Directivity is given by 6L over lambda. Length is available, lambda is available. So D can be found. In the present case, it is 8.7. It can be expressed in dBs too by applying 10 log over 8.7. It turns out to be 9.39 dB. So all the things that are asked to find, minimum number of directors, length, and gain, all the things are found. We move to another problem, example 2. A 75 megahertz Aggie array is to give a gain of 15. Determine its length and minimum number of directors required. Solution: to give a gain of 15, array length required can be found using this formula. D equal to 6L by lambda. So L is D lambda by 6. D is 15. So L becomes 2.5 lambda. Let us suppose n directors are required. Assuming typical spacings, that is reflector spacing of 0.25 lambda, director spacing of 0.30 lambda, the array length becomes, this is array length, 0.25 lambda plus 0.30 lambda n minus 1. Now, number of directors can be found as equating the length found from the spacings and the length found from gain. These two lengths. By equating these two lengths, we have an equation. Solving this equation, we get n as 8.5. So the number of directors then is 9. You cannot have half director. The length of array then can be found once n is known. Substituting n value in the expression for length, we get length as 2.65 lambda. Wavelength lambda corresponding to 75 megahertz is 4 meters. So length of array is 2.65 into 4, 10.6 meters. Earlier we found length in wavelengths, in terms of wavelengths. Now length is obtained in meters, 10.6 meters. Another problem, example 3, this is also set on Aggiora antennas. Calculate lengths and spacings of Aggiora array that has a directivity of 12 at 145 megahertz. Also determine the length of array in meters. So this is a typical problem. We are asked to find the lengths and spacings of elements. Directivity required to be provided by the array is 12. Frequency of operation is 145 megahertz. We are also asked to determine length of array. Here it would be more clear if we add elements. Lengths of elements, spacings of elements. Solution. Lengths and spacings can be estimated using the formulas. Length of driven element is 0.48 lambda. It is 144 over F frequency. Frequency is given 145. It turns out to be 0.99 meters. Similarly, length of reflector. It is 0.49 lambda equal to 147 over frequency. It turns out to be 1.01 meters. Length of directors. They are 0.45 lambda equal to 135 over frequency equal to 0.93 meters. Reflector spacings 0.25 lambda equal to 135 over frequency. They turn out to be 0.52 meters. Director spacing 0.30 lambda equal to 90 over frequency. In the present case, it is 0.62 meters. So these are lengths of the elements. To give a gain of 12, array length required to be from this formula. Frequency is given, so lambda is available. Directivity is given, so L can be determined without any difficulty. In the present case, it turns out to be 2 lambda. Let us suppose n directors are required. Assuming typical spacings, reflector spacing of 0.25 lambda and director spacing of 0.30 lambda, array length becomes, this relation we have used in the previous problems too, so no difficulty in understanding. Now the number of directors can be found from this relation. L is 0.25 lambda plus 0.30 lambda into n minus 1 equal to 2 lambda. Notice this 2 lambda is calculated from gain considerations. This length L is calculated from physical spacing of elements. Equating these two, we get n equal to 6.83. It means number of directors required is 7. When we consider 7, the length of the array becomes 2.05 lambda. Gain gave length of the array as 2 lambda, whereas some practical considerations are also taken into account. The length has become 2.05 lambda. Wavelength lambda corresponding to 145 megahertz is 2.07 meters. Hence, length of the array is 2.05 into 2.07. It turns out to be 4.25 meters. Another problem, example 4. This is also on Aggie array. Design a 6-element Aggie array functioning at 500 megahertz with a folded dipole feed. Estimate its gain, length, and also frequency boundaries of operation, assuming a 4% bandwidth. Solution. Lengths and spacings can be estimated using the formulas. Certain formulas are available. They give approximate spacings, approximate lengths of the elements. So they don't give exact values. They don't give exact design approximations. Length of driven element is 144 over F. In the present case, it is 0.28 meters. 288 meters. Length of reflector is 147 over f frequency. In the present case, it is equal to 0.294 meters. Length of directors, it is equal to 135 over frequency. In the present case, it is equal to 0.27 meters. Reflector spacing, it is 135 over frequency. In the present case, it is 0.15 meters. Director spacing, in the present, it is 90 over frequency. In the present case, it is 0.18 meters. So these are some approximate dimensions and spacings of the elements. Number of directors in 6-element array are 4. When typical spacings of reflector spacing of 0.25 lambda, director spacing of 0.30 lambda are assumed, array length becomes this one. This formula we have used already. So from physical considerations, length becomes 1.15 lambda. The gain of this array can be found from this formula, D equal to 6L by lambda. This is also standard one we have used in the previous problems. So substituting the value of L in this expression, we get D as a 6.9. Wavelength lambda corresponding to 500 megahertz is 0.6 meters. Hence, length of array is this one, 1.15 into 0.6 equal to 0.69 meters. Now, given 4% of central frequency is bandwidth, it corresponds to 0.04 into 500, 200 megahertz. Hence, lower and upper frequency limits become 490 megahertz and 510 megahertz. Here, bandwidth is given as 4%. Central frequency is 500. So 2% that side, 2% this side of 500 megahertz is bandwidth. Another problem, this is also on Aggiora antennas. Example 5. Design a 145 megahertz Aggiora array that has a directivity of 12 dB. This at is superfluous. So problem is design a 145 megahertz Aggi array which is able to give a directivity of 12 dB. Solution. Required dimensions, approximate ones, can be found using formulas. Length of driven element is 100.48 cm. Here we used formulas. These formulas are in terms of feet. These are same as what we have used in the previous problems. Here they are in feet, these are in meters, except that there is no difference, the same formula. So length of driven element becomes 100.48 cm. Length of reflector becomes 103.42 cm. Length of directors 97.01 cm. Element spacing becomes 29.85 cm. Length of array. These are dimensions of the elements. Length of the array can be found from this formula. L equal to d lambda by 6. D is available directivity. Lambda is wavelength. It is available. 145 megahertz frequency is given. So lambda is C by F. C is 3 into 10 power 8. Frequency is 145 megahertz. So lambda is available. Directivity is available. Substitution gives length as 4.138 meters. Another problem, example 6. This is also on Aggi arrays. Design a 6-element Aggi array for operation at 500 megahertz with a folded dipole feed. Find the gain, lengths of reflector element, driven element, 4 director elements. What is the spacing between reflector and driven element and director elements? Solution. Required dimensions can be found using the formulas. As already mentioned, in this problem as well as in the previous problem, the formulas are given in feet, or the formula give the dimensions in feet. After getting the dimensions, we have converted them into centimeters because we are in MKS system. Length of driven element is 478 over f megahertz. Present case it becomes 29.14 cm. Length of reflector is, formula is 492 over f megahertz feet. In centimeters it becomes 30.42 cm. Length of directors Formula is 461.50 over F megahertz feet in centimeters. In the present case, it becomes 28.13 cm. Element spacing, it is given by the formula 142 over F megahertz feet. In the present case, it turns out to be 8.66 cm. The gain or directivity can be computed using the formula 6L by lambda. Length of the array. This is length of the array. This is lambda. So substitution gives us D as 4.33. One can have it in dB2. In dBs it is 6.36. Now one point, how this 5 into 8.66 has come into being. This is reflector. This is a driven element. 4 directors are there. So spacing is 8.66 cm. So naturally, this is 1, 2, 3, 4, 5. 5 into 8.66 cm becomes length. 60 cm is wavelength corresponding to 500 megahertz. So that way, this problem solution has come into being. With this, we come to an end to the present session. To recap, in this session, we considered several problems. Some set on helical beam antenna and some set on Aggie array. Problems on Aggie are mainly concerned with the design aspects, whereas problems on helical beam antenna, they are mainly connected with the physical structure of the helix and directivity beam widths. Hope this session is useful to you. We meet again soon with a new topic in another session.